Today's learning goal is to calculate displacement and distance traveled. Calculate displacement and distance traveled. All right, so let's start off with a little bit of motivation. Our universe is full of moving objects. There's lots of things in our world. So, for example, planets moving around the solar system, asteroids kill the dinosaurs, so we might want to know where those things are going to be in the future. Cars moving around our highways, right? We want to know how fast they're moving. People, we just watched the Olympics this summer, so you might want to know like how fast somebody runs or how like fast a tennis ball serve is. Vibrating atoms. There's also the world. There's also like a microscopic world around us, and knowing how these very small particles behave is also like very interesting and very useful for modern technologies. Airplanes flying through the air. Anyway, this is just a small list, but the list is very long, and that's our motivation. So we want to describe the position of these objects. And the way that we do this is relative to some reference frames. So to describe the motion of these objects, we must define position. Position is where an object is located at some point in time relative to a frame of reference. And the frame of reference is something that we can choose, although some frames of reference will make your problem easier to solve. So that's something to keep in mind. But for example, take a look if you're trying to describe the position of this piñata, this like hanging object, you might decide, okay, I'm going to measure it with respect to the ground. So it's 2 meters above the ground, that would be its position. Somebody else might say, I'm going to measure it with respect to the ceiling. I'm going to say that the ceiling is my zero, my reference point, and that the piñata hangs down -1 meters from the ceiling. Both of these are fine. We just have to make sure to specify what we're measuring relative to. As long as you do that, you're going to be in good shape. Okay, next, let's define this thing called displacement. So displacement is a change in position of an object and in which direction. So this is very important. It's both the change in the position and the direction in which the change occurred. So we can write this a little bit more formally using an equation, this like physics formula. Delta x is the displacement. Delta is a Greek letter. It looks like a triangle, like an equilateral triangle, but it's a Greek letter, delta. And delta in physics means change. So this is the change in the position or the displacement. And it's all one single symbol, even though it's made up of these like 2 letters, right? We look at this as one symbol. We don't split it up. So this is the change in the position. Similarly, over here, xf, this is one single symbol, so it's an x with a little f next to it. It's a label telling us that this is the final position, and xi is the initial position. So the displacement is the change in the position, right? We have to do final position minus initial position is the change in the position. Okay, and in physics we use the SI units. The base units for length are meters, so all these are going to be in meters. All right. Now take a look at distance. So this is now, let's see, the magnitude of the displacement, right? So this is how far from the start. Notice the difference between these two things. This one is a change in the position. This one is also a change in position, but displacement has direction associated with it, where distance does not. Distance is the magnitude of the displacement. So it's just how far the object moved. We're not interested in which way it moved. We just want to know how far it moved, then that's a distance. If we want to know how far it moved and in which direction it moved, then we're talking about displacement. And this is something that's going to come up again in the future. And this is the idea between the difference between a scalar and a vector quantity. So in physics, we often deal with vectors. Vectors are quantities that have both a magnitude and a direction. Scalars just have a magnitude, they don't have a direction associated with them. So take a moment to think about which one of these is a vector, which one is a scalar. Right? So displacement, since it has a direction associated with it, this is going to be a vector. Distance has no direction, it's just a magnitude, then that is a scalar. So distance, scalar. Distance traveled, this is a little bit of a different concept. Distance traveled is the total length of the path traveled between 2 positions. So if you like started somewhere and then took this like meandering path around like a trail in the forest and then got back to your original starting point, the displacement might be 0 because you started where you ended. But the distance traveled is obviously not 0. You went on like an entire hike through the forest. Okay, let's continue. So we're going to look at some examples. Here we go. Example number 1. We want to take a look at the situation. Imagine you start at your house. You leave your house, you visit a tree that's 6 meters away from your house, and then you move back to your house. You like sit down in the grass, for example, halfway between your house and this tree. So the initial position, let's say, is at 0. The final position is over here at 3. So we want to know, what is your displacement? So let's like do this together. First step should always be to draw a picture. We already have a picture provided for us, so that's done. Next, what is your displacement? We're going to write down all the given information. So our given information is that we end our trip at x equals 3 meters. So x final, our final position, is 3 meters. Our initial position is 0 meters. So let's write down x initial equals 0 meters. And then we're looking for displacement. If you remember from our equation earlier, displacement is written as delta x, the change in the position. So this is what we're looking for. So let's write down a question mark so we know what we're looking for. And now we're going to select an equation that has all of our given information and also like the thing that we're looking for. So here we're looking for displacement, and we're given both final position, initial position. This is going to be the displacement equation that's going to work for us. So let's go ahead and write that down. Delta x equals the final position minus the initial position, and then we're going to substitute in our values. Final position is 3, initial position is 0, 3 minus 0 is 3. So we're going to say that the displacement was 3 meters, but we have to watch out because that's not complete, right? Since displacement is a vector, we also have to specify in which direction it moved. So in this case, we can say that it moved in the positive x direction, or you could say to the right in this case, right? Either one of those, but we do have to specify a direction. So let's say 3 meters to the right, or in the positive x direction. You get that little hat on top of the x, says it means the x direction is a unit vector. We don't have to get into that, but this is how we write in the x direction, the positive x direction. Okay, so next question, now we're being asked, what is your distance traveled? So now take a look. The distance traveled is more than 3 meters because you went all the way to the tree and then back towards x equals 3. So first we have to move 6 meters towards the tree. So 6 meters towards the tree plus 3 meters back. Distance is always positive. So 6 plus 3 is going to give us a total of 9 meters that you moved. And distance traveled is a scalar quantity, so we just have to say 9 meters. We don't have to specify any sort of direction. Okay, here's one for you to try. Then you start at your house, and you go to school, you walk to school, you stay at school for a while, right, during the day, and then at the end of the school day, you go back home. So your initial and your final are at the same location. What is your displacement? So let's, even though maybe it's kind of obvious to you, let's take the time to like do all the steps. So our initial position is 0 meters. Our final position is, let's see, we came back to the house, so also 0 meters. Our displacement is what we're looking for. So let's go ahead and write down our equation. Displacement is the change in the position, x final minus x initial. So let's see, x final, let's substitute in our values, 0 minus 0. 0 is our final point, 0 is our initial point, 0 minus 0 is 0 meters. And let's get into the habit, even though here it doesn't really matter so much because we didn't really go anywhere. But we should get into the habit of specifying a direction. So we can say 0 meters to the right. Although the direction is sort of arbitrary here at this point because our displacement was 0. So obviously it was a long day at school, right? We didn't just stay in our house, we actually did travel a long distance. So first you had to move 100 meters to get to school. And then later at the end of the day, you have to go 100 meters back to your house. So 100 plus 100 is going to give us a distance traveled of 200 meters. I highly recommend that you try all these problems on your own before watching my solutions, because the best way to learn is by actually trying it yourself. So what is the displacement? We have here, imagine a little fish that's hanging out in its house, little cave under the water, and it comes out of its house. It goes and sniffs a little piece of seaweed, and then it goes and hangs out with its friend, Mr. Crab, over here at the final position. So the initial position is at the house, the final position is over by the crab. So let's take a look. Our initial position, then it's going to be 0 meters. Our final position is going to be at the location of the crab. X final is negative 2 meters. And the displacement is what we're looking for, so we're going to write delta x. Delta looks a little wonky. Delta x equals question mark. So let's write down the equation. Change in the position, or displacement, is equal to x final minus x initial. So let's take a look. X final is negative 2. Substituting your values, negative 2 minus x initial is 0, so minus 0. So negative 2 minus 0 is negative 2 meters. And now we have to think about direction, right? So since it is displacement, we have to specify direction. And notice the fish moved from the starting point towards the left. Okay, so we can either say that I moved positive 2 meters towards the left, or negative 2 meters towards the right, or negative 2 meters in the positive x direction. Let's write that. So either negative 2 meters to the right, or positive 2 meters to the left. When it comes to direction and positive signs and minus signs, we have to make sure that it makes sense, right? So positive 2 to the left is the same as negative 2 to the right. Okay. And let's take a look at the final question, which is what is the distance traveled? The fish moved 2 units to get to the seaweed, or 2 meters to get to the seaweed, and then it had to come back to 4 units, or 4 meters to get to the crab from the seaweed. So that's going to be 2 meters to get from the house to the seaweed, plus 4 meters to get from the seaweed to the crab. So 2 plus 4 is 6 meters, and here it's distance traveled. Distance is a scalar, so we don't have to specify direction. Just 6 meters is all we need. All right, thank you for learning with me today. Great job.